Hello, how you all doing? Happy New Year and welcome to 2021. It seems to be starting on a grand track. Hopefully it'll begin to get better as we see life at the end of the tunnel with the vaccines and everything becoming available. But I hope you all had a nice relaxing break and a nice time as could be had with your families over the Christmas period and the New Year period. So today we've got quite an exciting embedded hour. We've got my really good friend Dan's going to come on. Dan actually works for Avnet in the US, but he's here today to talk about his sort of interests and his embedded career and some of his more interesting experiments and hobbies that he's done. I've also got a couple of things that I want to talk to you about beforehand, actually, before we go too far into that. And obviously, I like to sort of talk a little bit about what I've been up to recently. Obviously, Christmas has been and gone, so I've not done a huge amount apart from eat and drink. This week, actually, I have released a blog on GHDL, which is the free open source VHDL simulator. So if you want to take a look at my website, you can find how to get that up and running there, and that's going to lead on to a path where we start looking at the UVVM methodology and such like on there. So I think that's going to give us a nice path into looking into the verification side of things. The other one I actually wanted to talk about and make a little bit of an announcement about, and I don't know if Dan's on the call or not, but some of you may know, some of you may not know, but Dan Binnon and I and a guy called Sackett at the University of Lincoln, we've been working on a book for the last sort of 18 months on embedded system design, and all about our idea is we want to work all the way through from the initial concept of the board, so the initial requirements, the concepts, all the way through to designing the board, manufacturing the board, writing the software and the VHDL. And unlike most other boards, actually, we thought we'll actually design it as we go along. So as we've written the book, we've designed the board, which you can see here. So we've spent a good few days over the Christmas break. Actually, we did plan to do it in person, but we've been doing it remotely and bringing up the board remotely. So it's in a pretty good state now at the moment. You know, we've got the zinc on there, we've got the DDR up and running, we've got Ethernet up and running, the USB up and running, the SD card all checked out, and everything. So it's looking like it's a really the design looks like it's a really good board, and it's going to help us with the book. So you'll be seeing a lot this year. Actually, I'm going to drive you all up the wall about this book and about the concepts that we've got, because we think we've got quite a novel concept, we hope, of talking and presenting this book. And everything we do, you know, all the schematics, the layout, literally everything is all going to be made available. And along with the book, we will be also having a lot of blogs, webinars, videos, talking about the more in-depth, detailed aspects of the book, aspects of the board design that you can't put in the book. So I think it'll be quite exciting, and I really can't wait. Hopefully Dan's sending me one in the post at the moment. I really can't wait to get my hands on one. Literally, we've got these just a couple of days before Christmas, so it was a really nice Christmas present, and it was a really nice New Year's present to see that they actually powered up and worked like all new boards. So moving on, this week we've got, or this month even, we've got Dan who's going to join us. Dan, if hopefully your video and audio still works, so when we were checking a minute or two ago. And Dan's actually based in Hawaii, so he's got the shirt on it and everything, and everything for it. You sent me some pictures of your house the other day. It looks amazing. I'm not jealous at all as I look out of my window at the English winter while you've got the beautiful things of the Pacific. But Dan and I actually, we met. When did we first meet? We've kind of communicated over email for a while, but I think we first met in was it Lenaro Connect in Vancouver?
I think physically that's the first place we met, but I think the first time we communicated, I was working on SDSOC stuff, and you had already written some blogs on it.
Ah, yes, yeah, and you wrote and said I got them all wrong. Yeah.
Yep. Yep. And I was looking for some help, and you had the right stuff in the right place, and said, "Yeah, go ahead, use it." And sure enough, that kind of spawned off this whole projection of stuff I'm working on. So
that's good. But I mean, as we got chatted when we were talking about it in Vancouver, actually, like I said before, I'm getting old, so I'm getting forgetful. we realized actually, like, we might have been sort of like 5,000 miles apart, but our careers actually had actually been quite similar and we worked on a lot of similar type of applications. So you started out, because you sent me some pictures, and I am going to pull some slides up and show some pictures in a minute.
Sure.
If you started out working in the automotive world, this is after you graduated, so at university, so you studied computer engineering, is that right?
So I did computer engineering at the University of Buffalo, New York, and that's obviously USA. And from there, I was looking to kind of stay local to the area because my parents were still there, and I found a job at a company where we were creating automotive safety test equipment. So in the US and most other countries, you have to pass certain tests in order to sell a car legally in the at least here in the US, and Europe's got a different standard, but they're very, very similar. And essentially, we were building the machines to be able to rip cars apart, flip them over, throw them in the walls, specifically look for impacts, like to test airbags and things like that. And my job originally was to take this old NEMA system, which I don't know if any of your audience knows this. I know it's probably quite a few younger people, but think electromechanical, right? Not circuit boards. You're talking big wires, big relays. And my job was to take those systems and shrink them down to printed circuit boards.
So this is where you sent me this big picture of this big motor you were working on. I was just gonna
I don't have, because they were company proprietary, automotive industry is very protective over their stuff, but that's a similar motor to what I had been using. And essentially they weigh a couple tons. They're very large, but they are just a big electric motor. And essentially those are used to attach a car to, and you run it up to 30, 40, 50 miles per hour, or whatever the equivalent is in Europe. And you just run them into a wall and see what happens. So you instrument the vehicles, and it's more exciting than it actually is in person, because when you watch it in person, it just kind of goes boom, and that's it. But it's conceptually very exciting.
I think that's the case for a lot of engineering. You kind of the thought of it, the concept of it is actually a lot more exciting than actually doing it.
Yeah,
I think the one difference to that, I think, is tempest testing, which I think is the most nervous I think I've ever been when I've seen anything done that. So that's I mean, you sent me some pictures on this. So let me see if I can drag one of these up onto the screen, because this was quite interesting. But you got some huge, big sort of slides and big motors. Was it you got there with it to do it, or was that?
Yep.
Grab that picture now, and I'll pop it on the screen.
Yeah, I had a lot of lessons learned at that job, where there was some very cowboy-like engineers there, and like the one time I was checking out the motor, and I mean, that's exactly right, Adam, that picture. I mean, that's just for scale, that's the size of the motor. Again, that's not one I had worked on. That's just one I found online that was very similar. And imagine having your head inside the control box that takes, 480 volt, 3-phase, 1,000 amps, and you're trying to check it out, because of course at that kind of power level, you can't mess up. You have to make sure everything's correct. So I was sequencing the power up in various sections, and I had overridden some of the safety interlocks in order to allow me to check out certain parts of the system. And my the VP of the company came over. He said, "Oh, what are you doing?" And I told him I'm testing it out. And he said, "Oh, well, what's this?" And I had a potentiometer up at the top where I was controlling the control loop. And I said, "Oh, you can spin that so I can juice up different parts of the control system and try and see the feedback, make sure it's not going to self-destruct." And he's like, "Oh," and he grabbed it and he spun it to 100%. And it is the first time, like right now, I'm still getting goosebumps over it, but it was the first time I'd ever seen wires actually dance on the ground, because you pulled so much power so fast.
Yeah.
It was absolutely insane. And he was banned from ever coming in a building when I was working on that stuff, because I mean, I could feel like my hair, everything, just the field inside that box. It was scared me to death.
So did he? I take it he survived the encounter. Then I don't think I'd have been quite happy with if.
No, he got a good tongue lashing, but being the VP of the company and nothing really happened. But it was scary. It was a lesson learned. Always be safe with what you're doing. And you get to see some really cool stuff.
Yeah, I mean,
yes.
I think that's one of the key things. Actually, it's the lessons that you learn when you're not sort of the non-engineering lessons or the maybe the wider engineering lessons, shall we say? About safety and making sure that every obviously everybody wants to go home every evening. It's always good to try and consider about the safety and the aspects. It's really, I don't know, a few years ago when I was a chief engineer at E2V, we were setting up a new lab and I had to sign off a lot of safety things, and there were some chemicals that could be explosive, and I was really kind of like quite concerned about this. If I don't do this properly, I'm going to probably end up in jail if something goes wrong. So it's good that you start to learn that throughout your career and think about it. And the VP should have known much better than that.
Yeah, he's been known to be very cavalier with stuff. I mean, understanding the scope of things. I've got a great appreciation for that. We were doing a 207-210 test system, which is you put seats onto a frame. And then there's hydraulic cylinders that come in and you pull the seats. It's called quasi-static testing because you can't properly test, crashes and things all the time. So they have certain profiles that the seats have to maintain in order to like the seat will crumple a certain way very specifically to try and save the passenger. Because that's the goal, right? Sacrifice the vehicle to save the people. Yeah. And I was told all we were doing was showing the system power up and do some very basic testing. So I told the welders, just make me a little A-frame, just tack weld it in, just do something fast because the customer's coming. And nope, the VP, same guy. He's like, no, let's take it to destruction. I'm like, no, we don't want to do that. He's like, oh yeah, let's. So he hit that button. We had 90,000 pound-feet of force on this thing. And it was a 3-inch or 4-inch I-beam. And you're talking that much force on this thing, the beam crumpled into a pretzel, flew through the safety cage and embedded itself in a wall like 20 feet away. It was like, what? Just stop.
It is a good job there was nobody.
It was great.
Around or stuff behind that. So I take it this was a fair while ago, maybe. Maybe.
Yeah, this was
some time frame on it. It was when? Sorry.
Yeah, it was 2003, somewhere in that range, 2003, 2004.
So not too long, in my mind, not too long ago, but actually in reality, sort of 17 years ago now.
Yeah. And again, it was my first job. I mean, stuff changed. It was a matter of learning how to be adaptive to the environment because, I was brought on to do one job, but when other engineers and personnel shifted around, they put me in different responsibilities. And, I really learned a lot, really did a lot of really interesting things, did a lot of team leading that was kind of sink or swim on a lot of it. But it was really my first experience at being a high level professional. I wouldn't say senior because I was still kind of fresh out of college, but, a more senior guy where we're involved in trying to figure out, solving real problems. And that was really a good taste of that. And that's really what engineering to me is that, there's things in the world that need to be accomplished for various reasons, and it's our job to figure out what the solutions are, what the best way to get there is. And of course, unlike scientists themselves, we have to worry about, that whole fiscal thing because they want the world, they want all this stuff, but it's got to be as cheap as possible. And that's always the hard constraint.
It's got to be done for £3.50 and available next week. Yeah. Well, sorry, $5. It's got to be done for $5 and available next week.
Yeah, and that's actually, kind of like my second job. It was creating voice over IP telephone systems, and that job was that where we would spend $10, $20, $30,000 of engineering time to reduce one resistor off the board because you're making 10, 20, 30 million of these things. That one resistor, they'll save 100, 200,000, and it was worth it.
Yeah, it's always quite interesting when you think about that. I mean, my background is slightly different because I've never really done any sort of mass commercial production like that. I think I think the biggest production run I've ever been involved with was a few thousand. But it's a real different mindset when you want to run that. When you want to remove, when you're asking yourself every question: is this resistor valid? Is this resistor valid?
Right.
Is this capacitor
Right.
really needed? Do I really need this? Do I really need this component, or is it something that I can get away with? And we're quite. I guess I'm quite lucky because on sort of the projects I've worked on, it's never really been a huge. Obviously you've got budgets and you've got targets, but trying to invest 30,000 to sort of engineering time to design a board, to respin a board, to remove a resistor. It's interesting. It's quite an interesting thing.
No, and it gave me a pretty good experience. It's not, I don't think you're missing out. I mean, I don't think you feel that way, but I don't think you're missing out. It's that kind of engineering. It's satisfying in itself, but it's really not as, great as some of the stuff, we've been working on, just the lower volume, but higher specialization of stuff where there is, I've done thermal camera systems, those are always expensive, radios, satellite communication stuff. And, the big thing that I always try and express to people is that while I've had all this experience and seen all these things, it's because I understood the base of what it is. It's not that I understand satellite communications or thermal imaging cameras, or in the case of what I do right now, while I understand the electron flow through the chip and, timing constraints and all this, it's not that. It's that I understand the base of how the doping of the silica works, and you can take that and derive everything else. I mean, the radio works a certain way because electrons propagate a certain way. You can figure that out. You don't have to know that right up front.
No, you're quite right. I mean, I think people overlook those basics. And I think that's quite a good. I know we were talking just before we started about the sort of the few episodes of this that Max and I had done where we were chatting about sort of what to help you do if you're looking for a career and things, and it's quite interesting that you never, very similar to you, I've worked on a lot of things, from sort of submarines to medical things to satellites to all these things. And generally when I applied for the job before I became a consultant, I probably got no idea about the end application or what it was involved, apart from the fact that it was cool and I wanted to work on it. Because, but what gets you through the door, is not your specific domain knowledge on that thing. Having read about it a little bit before you go to the interview obviously is a good thing, so you can explain it and talk about it. But what gets you through the door and gets you the job actually is understanding the basics. It's fundamental. It always comes back to that. And embedded, I've talked with people about sort of, because I've done a lot of, like you, I've done a lot of things in like thermal imaging, in satellites, in aircraft, in submarines and such like that. And you know what it always ends up being? It always ends up being a black box with some connectors on it. It's always a black box with some connectors on it. And it's all about how you can design that embedded system. Is it a processor? Is it an FPGA? Is it a combination of the two? What are the interfaces?
Right.
It's those basic good electrical sort of design skills and system skills, I think, that are quite important. And you're kind of reiterating it there, and I'm rambling now, but it's good. So you moved on then into your second job in network and equipment. So that would be 2000. When did you move to do that?
That's probably about 2005, 6, somewhere there. It didn't last very long. The company was. I was
going to say, was that kind of tech boom, sort of when the collapse? Well, that was probably a couple of years earlier.
No, it was after that, but it was a poorly managed company. I don't want to obviously speak ill of somebody else, but we'll put it this way: they stopped paying me, so I kind of stopped working for them. So they.
I want to stop working for someone, and they carried on paying me. That's a much better. That's a much nicer situation to have.
Yeah. No, they but that was quick. That was the only time I'd been unemployed for any length of time, and I used a headhunter to find my next job, and headhunters can be good, they can be bad. You got to watch out. They have a selfish motivation sometimes, but if you find the right people, they're very good. They've got some very good contacts in the industry.
Yeah, I mean, headhunters is an interesting thing. Recruiters, as we call them in the UK, they're quite interesting. They have I mean, they make a lot of. In fact, the richest man I know actually is a recruiter for teachers. Believe it or not. But they have a real bad reputation because to them it is just a, if you find the right one, it's really, it's really good, and they can help you,
Right.
they can help you find the job, and they'll work with you. But if you, to majority of them, it's literally just, it's just a numbers game, really. At the end,
Yes.
it is literally just I have to get in as many resumes, as many CVs, get as many people in front of them as I can for the interview, and hope that one of them is going to get the job. And if they get the job, I get 25% of the first year's salary.
Right. And that's always the trick, right? Is you got to be careful with that, because if you find something where it is just numbers, it's, I don't know, you don't want to be a commodity. You want to be who you are. You are, no one else has got the experience that you have in the way that you have it. And you need to be able to make sure you can sell that to your, soon to be potentially employer or your current employer, and really show that, you're not a commodity. And that's really a way to stand out and, show people how good you really are. And, but that's where I got into my next job, where, I was doing thermal imaging cameras, and this whole kind of software defined world that we're in right now, it was interesting because that was my first exposure to something like that, where we were actually using FPGAs to put different thermal heads on our processing board.
Mm-hmm.
And what's interesting, while that company had its own fiscal problems, which is why I left there after a few years, it was really interesting, some of the high technology. I mean, I'd never worked with a 12 or 14 layer PCB before. Now it's like, oh, if it's not 20 layers, that's, not special. But, at the time, I mean, 12 layers, that was absolutely it was a weird number, because, the stack ups have to be certain multiples. But it was something that we just, I don't know, to this day, I'm still very fond of that system, where, it was also my first exposure to satellite communications, and you get into some of that military stuff where, it's just, wow, people really do have technology like that. It's just not, typically exposed to the general public. And it's just amazing the way that if thermal technology wasn't expensive as it was, the kinds of benefits that I think we would have are huge. I mean, you can detect cancer with it. You can do, breast cancer screening and things without having to go through all the pain of current systems. You can detect just medically so many things with thermal, because, like, consider cancer. That's a really easy one to talk about thermally, where what is cancer? It's an uncontrolled growth of cells. Well, that produces a lot of heat. And you can see those patches when you look at people without having to do X-rays or MRIs or any of those things that can cause, damage to you because of the radiation. This is just looking at radiation you're already producing. But it's interesting technology.
I mean, I always liked, I did actually bizarrely around the same sort of time, around 2006, I did some work in thermal imaging as well, work again with FPGAs. We were using the Vertex 2 Pro with the with the PowerPC 405 with the PowerPC 405 inside them.
Yep.
But I really, it's funny, the weirdest thing about sort of imaging, thermal imaging, whatever, is to this day nothing quite gets me as excited as an engineer as seeing a picture you've created on the screen. And it might just be a simple, it doesn't have to be running a complicated algorithm, but that first time you see a picture on the screen and it's just a sort of a pass through or something, or a thermal image, just a thermal image pass through, and you go like, it's pretty cool, that really. It's obviously, I mean, thermal imaging, actually, when I worked in thermal imaging, I don't know, obviously you'll know this, I presume you were using some of the more exotic semiconductors for the thermal imager. And they have a really non-linear response to thermal to the thermal photons and such like.
The microbolometers are not linear.
Yes. So you do. And with the one I had, we had a little project where we actually did some machine learning, some really early on sort of AI, to actually learn the calibration parameters required for each pixel on the board to get it up and running, which I thought was really quite interesting.
There you go.
Oh,
even to this day. I don't know how well that's going to show up.
Yeah, I can see that. Yeah.
Yep. You got to have toys to play with, Adam.
Which one's that? Is that one of those little Fleur leptons or a?
Yeah, it's a little FLIR from I think Foxcam makes it. But that's one of the cool things about my current job. We're skipping one, but yeah, I get access to all sorts of cool toys and stuff, and it's just a little, I don't know how well that's going to show up, but it's just that little itty bitty finger for reference.
So we've put one of those on the board I was talking about. That at the start of this, we've got a FLIR Lepton 3, a little FLIR Lepton 3 on the board, and I've actually got if you've got a Z board, if you've got a pink board. Plug in my repos now, but I've got a FLIR Lepton overlay for the pink Z1 and Z2. That if anybody wants to play with one with the pink, you can go and download that overlay. And all that.
Is that for the P mod or?
They have a little breakout board. It's not a P mod. It's kind of maybe 6 pins for what's it got? It's got video.
You're talking this guy then.
That's the one. Yeah. So if you've got one of those and a pink board, you can plug it into the Arduino header.
Okay.
Into the right position where the SPI, the I2C is, and then I did a little overlay for that allows you to, that it does it all and just gives you the picture. I do love little playing with little thermal images and thermal.
Yeah. Well, especially, I mean, years ago, this, like I said, this is maybe, I've been here 10, 20, I don't know, 12, 13 years ago, whatever it was that I was doing this stuff. I mean, the thermal heads were much, much larger, but they were also much higher quality. This is, I don't even know what this thing is, but it's got to be like 160p or something. It's small.
I know what they are. They're quite a weird one. They're 120 pixels by 100. 120 pixels by 160 pixels.
Okay.
Put video out at 9 frames per second over SPI.
Yeah. Well, hey, it's easy and it got the price down. I mean, that was like I had mentioned earlier. The prices of thermal are so high that, like, the systems that we were using, the heads themselves were about $6,000-$7,000 a piece. Just the head. That's not talking any electronics, the body, the intercoolers. Yeah. Because that's, just a little education for the audience. With thermal cameras, the biggest problem is they see themselves because the electronics self-heat. So you have to account for that. And it's a really interesting thing to try to do, especially when you're garbed up in your, clean room suit and you're trying to, just get it to work. It's like, and you got all the heat going on. It's like, it was interesting, but the
best one is when people try and see pictures and they try and get some pictures and they point it out the window, forgetting that IR doesn't transmit through the
certain IR, right? Long wave IR, because you have three different commands. Yep, shortwave and midwave will pass through long, and in fact, that's actually, if you think about it, that's why your car heats up in summer when the sun's on it. The long wave gets blocked, but the short wave passes through. It hits the car seat and interior, and then the seat radiates long wave back out, and then it gets trapped inside the car. That's why your car heats up. It's,
So you can learn something on every one of these episodes.
Absolutely.
Even if you want to or not, you'll learn something. So thermal, so what kind of was it all FPGA based or was the software processing based?
Well,
or was it?
Yeah, so we had a couple of processors that handled the day-to-day stuff, dealing with your different things like Wi-Fi, Ethernet, serial communication. The FPGA was really there to do the heavy bulk lifting. We reprogrammed it to, we had a standard header that we would use, so you could swap the entire head with our adapter board, and then you just put a different FPGA image in. Now, this is pre-Spartan 6 days, so what was that? The L3000 or LS3000, something like that?
There was a Spartan 3, weren't there? There was a Spartan 3.
Maybe it was Spartan 3. I just remember it had a 3000 in the naming scheme.
Yeah, so it'll be a Spartan 3.
Yeah.
They were good.
And essentially we use that as a big multiplexer to switch around the IO. If the sensor had, different manufacturers want their 16-bit output at different locations, or they're doing this, or different kinds of clocking schemes. Because unlike visual modules that have been around for so long, and they've kind of standardized on, one of like 3 different formats, the Sony format, or I forget the others. I think Fujitsu has one, and there's like one other one, and it's like any visual sensor you have is one of those 3. But then you look at thermal, it's just, everybody did their own thing. And so we use the adapter board, it goes into the FPGA, and from there we did it was probably the first ever exposure I've had to some very basic AI stuff, where they did this thing called tripwires, and you could have this thermal camera pointing at an area for like a security application, and it would look for a tolerance on the pixels, and you would set up a single wire. So this way, if you were, say, for example, watching a crossing, if something came across that wire, it would trigger, and then the whole system would wake up, snap the images, send it over Ethernet or satellite or whatever it happened to be. And, it was a security camera application. Think like prisons, military, airports, things like that, where, the only thing that you have to worry about are, like in the desert, for example, you'd have to worry about twice a day the camera goes blind, because if you're looking for people at 100 degrees body temperature and the temperature outside comes up to 100, you can't differentiate the difference, right? But we had some special stuff we did to get around that. There's, that's all proprietary. I think even to this day, it's proprietary stuff. But there's tricks you can do with thermal cameras. Again, being a microbolometer based, if you think about it, it's just I hate to say it's like a thermopile, but I guess technology-wise, think of it that way. But it's more sensitive to certain bands of the thermal world, and you can do things to integrate across the signals, to add some capacitance, clock it in different ways, and you can trick the silica to actually behave in those specific instances. Of course, there is never a free lunch. You give something up, you give up some resolution, but in doing so, you can pull out some definition.
Information, yeah.
Yeah, exactly. So
I'm a big fan of film. I love playing with film. That's why we found Dan keeps telling me off Dan Binham keeps telling me off for asking about sort of for requirements creep on this little board that we did. But I was like, we must have a thermal imager on there. We've got to have. There's got to be a use case we can find to justify having one.
Yeah,
having one on there, which is the case. So I'm quite looking forward to it to play with that again. Because that's the FLIR. We've got the same one you've got, the FLIR 3. The one I've got at the moment is a 2, which is half the resolution of the one that you've got. So
I think the most interesting I did thermally, because these are all vanadium oxide based, but the company I was working for, we had so every thermal camera out there pretty much is vanadium oxide based. It's some sort of combination of vanadium, some oxygen modules, and various combinations with some other stuff, and that's what makes it sensitive to thermal. But the company I worked for, we actually had something based on amorphous silicon, and it was their own design. So what was interesting about it, because of the way patenting and laws, I mean, this is kind of the nasty side of this. Honeywell did all this development years and years ago under, secret contracts and things for the military. And then once the secret was lifted, the next day they patented all the technology. So everyone in the entire world that wants to create a thermal system has to pay royalty to Honeywell, unless you're doing amorphous silicon, which is kind of cool, because that doesn't fall under the patent of vanadium oxide. And the whole point was we were trying to create these visible thermal sensors that were really cheap. So say, for example, conference rooms, looking for people, security from the standpoint of not looking for identification, like, hey, that's Adam Taylor, but to know there's a body in this room that shouldn't be here, that kind of identification.
Yeah, that makes sense.
But, I don't know whatever happened to that. I left the company before that went anywhere. So
you you had some time on thermal imaging, and then you moved over into military communications. So I'm presuming this is, you can't talk too much about this, and we'll not talk about this is sort of like RF communications, like frequency hopping type stuff.
Yep. All the frequency hopping stuff, the military channels, satellite comms, a lot of electronic warfare stuff, which is kind of a funny name because it wasn't really I mean, I understand why they call it that, but it's not like what I was doing was damaging or hurting, or it was more protectionism and creating a safe environment for the soldiers and whatnot in the new crazy world we live in. And but yeah, no, it was some really, really bleeding edge technology. And that was where I think I really cut my teeth on some very, very high end stuff. You know, it wasn't a matter of cost. It was like you had mentioned earlier, it was a matter of performance. It didn't matter what the cost was. If you had to spend $20,000 on a component, you spent it. You did what you had to do to make it, you know, meet the objective. And you know, I won't. If your audience, if anybody wants to see that kind of stuff, certainly get involved. But I would suggest that it's really a pain, because invariably when you have to work in this kind of environment, you work in a locked room, a skiff, and you know, you had to check in, you had to log in, you had to do, it take you 15, 20 minutes just to get to your desk. And invariably,
not easy neither, can you?
yeah, and no phones. Although they're always willing to tell you can have a one-way pager, which I don't know who has those anymore, but but yeah, no, you spend the 15, 20 minutes, you log in and you put your stuff down, and that's when you have to go to the bathroom. So then you got to get back out. It's like, it was always a pain.
Yeah.
But,
it's a weird. I mean, the defense world, I'm sure, you know, I'm sure some people look at it. It is a really weird world to work in, just because of that sort of security. Yeah. I think the weirdest one I ever worked on, I worked on a missile program, and they used to have to tell the engineers, you know, literally weekly, there'd be an email coming around from the security department saying, stop editing Wikipedia with a real performance of this missile or whatever, because people would Google it, they'd see it, and then that engineer in them would kick in, and they'd be like,
yeah,
not true.
That's not right.
Just and edit it, and then somebody would go, do you think that might be secret?
Yeah. Yeah, no, it was interesting stuff. And certainly I think the vast majority of my FPGA experience came from that company, where, you know, I've done hand routing of FPGAs. I don't recommend that. I really don't, but I have done it. It was, you know, did some hyper routing where we had to meet some performance, and the silica on the parts just, you know, they weren't rated for that. But this is, again, it comes back to, this isn't, oh, please, sir, may I do this? This is, you walk up to a company like Xilinx or Intel or whomever with a briefcase full of money, and you say, we need it to do this, help us. And they do it. And you do some really, really absolutely amazing things where, you know, if I had to put a number to it, you know, there's a handful of people that I know that can do what I used to be able to do. I don't think I could do it right now, but, you know, where you're really getting to the point of worrying about electron flow through the part versus just, here's a constraint, let the tool do whatever it's going to do. It really was amazing. I mean, some of the stuff like Orca FPGAs, I can remember being locked under contract where, well, because of certification on the system, you're not allowed to change the code, but you have to add a feature. So you add certain things, and then you're sitting there, you've got 5 or 6 build machines running with random Cs, just building images over and over and over, trying to meet timing, because you're not allowed to do what's necessary to make it work properly. And it really pushes technology. I mean, I remember the one system we were working on, and I'll leave the manufacturer out because I don't want to, you know, endanger anyone here, but where we were using the DSPs. And for anybody who doesn't know, in an FPGA, the DSPs are high-end mathematical formulas, so that, or hardware accelerators, so that when you're doing math, you don't have to tie up all your LUTs and other resources that you can better utilize for routing and things like that. But anyway, the problem was we were using so many of them that they were the system was packing the DSPs next to each other, and the frequency that we were operating at happened to resonate or something, and it was actually coupling between DSPs. And I wasn't part of the team that discovered that, but there was 6, 7 people, which when you think about it, it's like, well, a lot of the companies out there, 6, 7 people is their entire engineering team. Well, you get to these large defense companies, they just keep throwing bodies at it until they get the problem solved. And I don't know how they did it, but wow, they went in and they found that it was doing that. And they went back to the manufacturer and said, you got to fix your tool to operate like this. And again, it's one of those, here's a briefcase full of money, make it happen. And they actually spun off their own special, this company's own version of their build tool just for that.
Yeah, I mean, not for that reason, but I've had similar in the past for high reliability projects where you've got a custom version of the tool that has capabilities to everything. So somebody's actually just asked a question in the comment about it, and I thought it's a good question. So saying when you're working on this when you're working in sort of like the defense world, the closed world, and you hit an obstacle like that, how do you go about and how do you go and find the problem? Because you can't even tell the manufacturer what 9 times out of 10 you can't even tell the manufacturer of the device what you're using their device for. So you get, well, I have my answer, but Dan, I mean, how did you used to tackle this?
Yeah, so a lot of the time, the end use is really the classified part, at least in my experience. So if I can go to somebody and, let's say there's a real defense application that requires a signal at 5 megahertz or something. I mean, obviously I'm making all this up. Well, I don't have to say why it's 5 megahertz, but I can go back to the manufacturer and say, look, I'm doing a thing at 5 megahertz. I don't have to explain why. That's the classified part, but the performance of the part, or you can also, having a lot of experts on your team, you can usually come up with a use case that matches what you're doing that's not classified. And of course, again, since you've got all these resources, you have an entire engineering team that can come up with this, prove it, validate that it's the same, and then take that public use case to the manufacturers to show them exactly what it is. Because a lot of the time you have to appreciate from both sides, having lived on both sides of this world. A company who manufactures a part, they want to know your use case in order to help. But the problem is you don't want them to know because they're also helping other entities that could be your competition. So you don't want them to know because you don't want that information kind of leaking back through to the other competition. So a lot of the time you got to be very careful, and a lot of the time you propose. I mean, it's not something like if you work in a company of 20 people, you've never seen this kind of a thing where we discover a problem. When I was at this large company, we discover a problem. It might be 4 weeks before we even talk to the manufacturer to tell them there's a problem, because all that time it's going through management reviews, team reviews. You're looking at how to approach the problem, how to express what the problem is. And sometimes you even have to get permission from the customer, because ultimately they're the ones that hold the classification. And if you need to release something, that kind of whole chain has to go through. And 99% of the time, there's agreements and classified people who have certifications for dealing with the stuff at the manufacturer anyway, where maybe somebody wrote the code in India or something that wouldn't be allowed to see this. But there is a group of people that have, clearances and things like that to be able to handle this, and they will be able to genericize it and work with the right people. So certainly it's slow is I guess how I want to express what this is.
Yeah, and I think actually slow describes working in the defense world quite well. Yeah. nothing is ever that fast, really. So let's leave, because we're running on, and I know you've got a hard stop because it's coming up to 7 a.m. in your morning time. So,
it's about 7. It's almost 8, so it's quarter to 8.
Yeah, so you've got a hard stop at 8. So you left after your military career. You went to work for Avnet doing the marketing role, which is how obviously we came into being. And that must be quite a difference actually from doing the sort of the detailed design work, the nitty-gritty design work, designing these really cool FPGAs, to kind of helping and supporting and marketing sort of
and the nice thing is, I mean, you say the word marketing, I'm sure a lot of your audience, they're cringing right now because engineers and marketing, it's like oil and water. But really, I'm a technical marketing engineer. There's a difference where my job isn't to market. My job is to create solutions that allows marketing to happen. So my job is really to look at like people in your audience, other customers, users of this technology, and really understand what they're trying to accomplish and help get them to that point. Sometimes it's called demand creation. Sometimes it's called, just helping the customers out. And so a lot of my job, while I don't get to the nitty gritty details anymore, I still get involved in a lot of technology, see a lot of things. I don't think I get as detailed as you get, Adam, but like right now, what I've got running in the background, because that's something to be creative about, right? You're creative with your time. I'm actually working. I'm letting the machine do the job while I'm busy having this fun conversation. But
really, no red going up, by the way, on your build.
Yeah, well, none so far, so that's been good. But yeah, no, it's really you need to be cognizant of people don't have the ability anymore or the time because to really understand those details. So a lot of what my job is right now is to work out that base layer. Let somebody who understands that technology, understands how to make their thermal camera work, understands how their specific, value add or solution really can be applied. And my job is to enable them, because while they don't understand how to create Petalinux images, or, maybe even they don't know how to turn on an FPGA, my job is to teach them that, or give them a basis to work on where they can just, do the coding for what they specifically need and create that solution. And that's really
so essentially you're kind of allowing people to just focus on their value added activity and not on to have those technological sort of hurdles at the bottom.
Exactly. So now they don't have to have an FPGA expert necessarily. They can have somebody who understands, like, especially using tools like HLS, the old SDSOC and the new Vitus tools. And I'm sure that Intel has got some stuff like that too. I'm not familiar with their technology. I work for Avnet, of course. But your C coding, I mean, everybody knows how to code C, and these tools can allow you to operate at that high level that our brains like to function at. And well, what is our solution? Well, I don't care that it takes a bit to go from pin 1 to pin 3. All I care about is that the right word is coming from my technology, my sensor, and getting into my algorithm, processing, and then making a decision based on it. And that's, really becoming more and more apparent as the AI stuff comes out, where, you've got these experts and these algorithms that I don't know how much experience you've had with AI stuff, Adam, but it just blows me away how complex some of this stuff gets. And I can run it. I don't need to know. You just turn it on. It's amazing.
Yeah, maybe we should get Mario to come on one of these and talk about his experience with AI, because that's quite a wide sort of topic area. But you're right. It's amazing. It's really AI is one of those. It's like everything in life. It's really simple. There's some really simple examples out of there. Once you start stepping outside that into into the actual networks and the training, and not just saying whether it's a cat or a dog or a apple or an orange, it begins to get really quite rapid, quite
right.
Quick. So a couple of other things I wanted to focus on, just because, like every engineer, you don't just limit yourself to electronics and such like. So you actually, so when we first met, you were talking about your home automation system, which you had when you were living in Buffalo, which just sounded absolutely amazing. Actually, it sounded like, and this was all pre-Alexas and pre-Google Nest and everything. You did it all yourself. So I don't know if you want to spend a minute or two and just explain what you had going there and how you did it, because I think that was quite cool. And then I want to touch on your metalwork and your making of go-karts and such like.
Sure. Yeah. So you're right. So prior to Alexa and all that kind of stuff, it's I had a completely self-created home automation system. It was based on some software written by a company called Homeseer, and all the logic behind it, the control. I'd say about half the electronics were self-made, where I had a custom thing I wanted to happen. So for example, I didn't realize it was called two-factor authentication, because this was even before that. But for example, my wife was working, she'd come home in her car. The car had a couple transceivers on it, and the house would actually reach out to the car. The car would reach back to the house and say, yes, this is who I am. And then the house would reach out to her purse, and she had a sensor in there, and say, are you there? And it would reach back. So by doing that, we had this kind of two-factor authentication. And by doing that, the house would know if we're home, who's home. And for example, she would come home and she'd walk through a different door than me, so different lights would come on. Her favorite thing was I hacked Roombas. So this is way before what they've got now, where Alexa, go vacuum. And when the house knew we weren't home, it would actually automatically, because I had a custom little Bluetooth board that I hacked into the serial port for the debug port, and the house would actually command the thing to go start vacuuming. And her favorite thing on that was we had one that we called suicidal, because it'd always get near the stairs, and the front wheel, when the front wheel dropped out, it would shut down so that it didn't fall or whatnot. It was a good design. But the rug was just gradual enough that it would get just on the hairy edge, and it'd be like in the middle of committing suicide every time we'd come home. So I fixed that eventually, but it was just funny that and it was cool because we were just both professionals. We didn't have kids, so I had a lot of time, a lot of money, a lot of energy to just dump into this stuff. And we would both leave, and the house would know that, and it would just take care of the house for us. We had the squeegee, the mop one for the kitchen, and the other vacuum around. And but the neat part was really the control of the lights. And until recently, I've always used that system as a way to save money because, you walk in a room, you leave a light on, you forget about it. Especially in today's world, you just get so busy, you forget stuff like that. And the system ran a computer 24 hours a day, but it saved enough in electricity that it paid for itself. And we got the benefit of having a full run server all the time. So it was kind of cool.
That's kind of exciting. So as long as you're home automation, I'm going to just share my screen again here. You also did some metal working as well, and you built a go-kart for you've got 2 boys, is it?
Yep. I got 2 boys.
So actually, I'm presuming that's your lad in the picture there, zooming about in the go-kart, and of course, full PPE was taken care of. I can see the hat in it there.
Oh, of course. that was the main requirement. But yeah, and the thing is, Adam, I use this kind of stuff as a teaching tool. The kids help me figure out the angles. They help me figure out the cuts. I worked it out ahead of time, so I knew what the answer was. But anytime we could use and like I'm sure you're talking to you, knowing you for as long as I have, I know you're similar to me, where being hands-on with stuff is so important for me to learn it. Like I can't just read a book and understand it. I have to do it. And utilize this as a teaching tool just to figure out those angles. And like, for example, think about it, the Ackerman angle, if you have 2 circles because you've got 4 wheels and they're trying to go in a circle, the inner wheels actually turn at a sharper angle than the outer wheels.
Yes.
You have to calculate the Ackerman angle and figure all that out. And the kids helped me with that. It was actually, it was pretty cool. But
they made them do math while they were having fun, yeah?
Absolutely. You gotta do that. And the thing is, you never know what people are going to be interested in. So you got to expose everybody to as much as you can. And they did some of the welding. They did, even at I think at that time, they must have been, maybe 7 or 8 at oldest. And, they welded, they cut that stuff. They figured out angles. And, even if it's just to get them an appreciation of what they don't want to do in life, that was really the goal. I mean, and maybe they like that. I mean, they don't have to be an engineer. They can go and become a metal worker. Welders make, depending on what you're welding, they make more money than I do. It's not that I make a lot, but you know what I mean? It's you can have a very, very good, well-paying job and not have to be an engineer. You can be, very, very intelligent and smart at doing welding. There's being good at what you do is really where the value is. And that's what people will pay you for.
It is. Well, you have to enjoy what you do as well. You have to try and kind of if you can make people find what they're good at, what makes a heart sing or whatever, then you never, I'm not going to say that you don't have bad days when you don't want to get up and go to work, because everybody does, but generally, you can do something that you love and be generally happy with it. So you built this go-kart, right. That looks really quite cool. But you also where's it gone now? You also did some machining and casting.
Oh, so, yeah. So that stuff is, that's lead there in that picture. You can see the L I punched into it.
I was going to ask what that was. Yeah, so that's lead. Yeah.
But yeah, and I do roses. I make those for my wife for various anniversaries and things. And I made them out of steel and copper. I have plans to make them out of brass and whatnot. But I've also done
a good one, I'm told by your wife.
I don't think I could. If I worked for you, I could afford it. I don't know about buying gold right now. But yeah, no, and it's pretty simple. I mean, you just got to be, coming back to what we were talking about way early on. It's just you got to be safe. Understand what's going on. Know that this stuff is not difficult. You just have to be careful because, while that lead is not hot by comparison to say aluminum or aluminium, depending on your audience. It still can damage you, right? It still gets hot enough. I mean, metal's a crystal. It doesn't want to be liquid. And if you're going to force it that way, it can be dangerous. But no reward for no risk. And, I've done a lot of stuff where, for example, I came prepared with props, But
Yeah.
this used to be a truck wheel. You know, this is the sprue where the aluminum got poured in. The form that we had here, I made it out of wood, and my friend helped me. Actually, he did most of it, teaching me how to do this. And but this actually is a second copy of this. So we turned it down. This is actually a pulley we made. So you got your through hole, and you put a V-belt in there. And the idea is to I want to make a powered hacksaw from scratch. So you got to make your own.
The one with the art, yeah.
Exactly. Yep. And I know I could go out and spend $100 and buy a bandsaw or whatever, and there's 100 ways to do it. But it's a desire to do it.
Where's the fun in buying one when you can spend a lot more time and money in building one? It's much more interesting, and it engineering, your engineering box as well, you know, and it helps you.
Absolutely, and even, you know, this is just a prototype, but I think you were going to bring that up at some point, but this is a pen I made.
Yes.
Which, you know, it doesn't look very good, but this is the prototype, because actually what's cool about it, most people make pens and they're static, you know, or they make it where you have to screw this end on or off in order to have the pen come out. And I didn't want to do that. So what I did, you know, taking inspiration from the cheap click pens, essentially I made my own internals here. There's actually a ball bearing in there, a special cut raceway, a pin that goes in to hold everything in place. And by doing that, you can actually, you know, you get you can see the tip coming out.
The tip comes out.
So it's, you know, I mean, a lot of really cool stuff you can do. I mean, it even looks weird because, like, I was experimenting with polishing here, but not here. I don't know if that's showing up. Yeah, I guess it is. It's
it did. You can just see kind of like halfway down it. Sort of the shine on it changes from being shiny to matte.
So, you know, I mean, just there's so many things you can do, and it's really just you work in a engineering process, right? That's what I really learned in life, is that if you analyze things in that process, you can always have good results. It's just how much energy and effort do you want to put in? Is it worth it? Or do you just, like you said, just spend the $10 and buy something that somebody else has made?
Jim's just made a comment in the things. He says he's spent a lot of time and money building stuff that he could have bought for a quarter of the price.
Oh, absolutely. You don't do this to save money.
I know, but you do it to learn and to educate, and you know, and it's interesting. You know, it's lovely it's nice to say. Every engineer I talk to, they've got their own sort of, you know, they have the electronic side or whatever, and then they've got a different side. Oh, like Adam Carlson, when he mechanical engineer by day, aerospace engineer, but then obviously he designs electronics by evening. So it's all
right.
All quite interesting. Good. Look, Wade, I'd better begin to wrap up with you, Dan, because you said you've got a hard stop of 8, and we're about 2 minutes, 2 minutes away. So thank you so much. Thank you very much for coming on and chatting with us. It's been great to learn about your career and what you've done, and your views on career development and the sort of little projects you've done around the side. And I'm just going to say it again, I'm really jealous of where you live. So once this pandemic's over, that's it. I've seen the photos. I'm going to book some flights, going to go and drink some drinks on the Hawaiian beach.
Yeah, absolutely. We'll take you to some of the special local places. And, you know, I got jealous when Max was wearing his shirt. But I don't know if his was made in Hawaii. Mine is made in Hawaii. So
yours, I will say yours is a lot more tasteful than Max's. Yours is a lot more tasteful than Max's. So I'm gonna wrap this up. So I'm gonna reach out to Jim as well at some point. I think Jim Burnham's just put some stuff in the comments. I'm gonna email Jim back now, because I forgot to do that before Christmas, and hopefully we can get him to come on. But yeah, Dan, thank you so much for coming on. We'll leave it there. The next one of these is on the 12th of February, I think. I'm not sure who my guest's going to be. Arm are supposed to be coming on, but they were off for Christmas this week. So hopefully we can get Arm to come on that one. If not, maybe we'll get Dan Binnon, my co-author, to come on, and we'll talk about the book. But I'm sure the next one will be just as well planned and well thought out as this one, where it takes spend at least an hour beforehand preparing for it. But everybody, thank you very much. Have a great month. Stay safe, and I will see you all next week. Dan, have a great day and weekend, and thank you again. Thank you very much. Bye bye.
Yeah, thank you. All right. Bye bye.